Okay, good morning. First, about the exam, your class pretty much nailed it on the head, getting a 75% average with the bonus points. Even with the 70-71% before bonus points, I probably wouldn't have rounded it. I usually only round if it is below a 70%. My Alkene 2 class had a 64% average. And their exam, don't tell them, actually had a lot of harvested questions from past exams, which meant if they had been going through the exam archive, they would have been really well prepared. And I would say the same about this one. If you'd gone through the exam archive, you should have been pretty well prepared. At the very least, there shouldn't have been questions that surprised you on our midterm. But your exam didn't have anything harvested, so the fact that it was right on a 75 is good. What you guys can see by the color coding is that 2 people got an A before the bonus points, and those bonus points took them over 100%. A number of people had Bs that moved up into As because of the bonus points. Some people with Cs moved into the B range because of their bonus points, but no one on the bottom half of the class actually changed their letter grade or had much improvement at all because of the bonus points. So bonus points disproportionately improve the results for those who already did well. And I don't like that very much. In fact, I've thought about taking bonus points out of my exams entirely because they are only helping people that do better. They are not helping people that need the help. And there's some debate to be had on whether it actually improves the learning experience or worsens the learning experience for people with test anxiety. If you have anxiety, it can make you more anxious. I've polled my classes over the years, and actually the majority of my students say it doesn't make them more anxious. It certainly doesn't help, but it's not something that they would advocate to remove. So I leave bonus points in, which disproportionately improve the scores of people that already did well. And because of that, I also give you guys the exam analysis opportunity, which disproportionately helps people that did poorly on the exam. So you can see someone with a 36, that's almost exactly half of the points from the exam. They missed 38 points. No, they missed 34 points. And that means they have the opportunity to earn back 17 points. But they have to earn it. Submitting an exam analysis is not enough to get you points back to the midterm. For instance, I've seen exam analyses that come back and the student will say something like, the correct answer for problem 2 is D. Although this surprises me because I would have thought the correct answer was B, but clearly because of what I was given back with my exam, the correct answer is D. So this is maybe why D is the right answer. And they misread the circle that they had put and the circle that I put. So they had put D, which was incorrect. The correct answer was B. But then they look at it when they're going through it and they're like, oh, I must have put that. They mistake it. So how many points do they earn back for the mastery of that problem? None. You didn't actually understand it? You psyched yourself out. You doubled down on the wrong answer, telling me that the answer that I circled was the wrong answer and the one that you circled was the right answer, just because you got confused, right? So this is not an assignment that I give points to lightly. This is an assignment where I am looking to see that you've understood it, that you've mastered it. And it does not matter how many points you earn back here if you do not know it before you get to the final. So this is not just an opportunity to improve your score on this exam. That is the least of your worries. This is an opportunity to identify the shortfallings you had. No? Is that a bad way of saying it? Shortfallings? Shortcomings? Sure. The weak spots that you had, the mistakes that you made, it's an opportunity to identify those. Because if you don't know what you don't know, how are you going to know it before the final? So it helps you identify your mistakes, and it helps you master those concepts because you will see them again on the final exam. Are there any questions I can answer from the exam? Otherwise, feel free to message me about them, or you can bring them up later.
We don't do analysis for the bonus points, right?
You can do an analysis, but you won't earn points back for the bonus points, because those were already not part of the grade. You didn't lose those points, you just didn't earn them. Please do the exam analysis. I implore you. Employ you? 50 bucks. Right, so do it, because it cannot hurt you. Even if you earn 0 of those points back, that is an opportunity to realize that you still didn't master it. Okay, actually, a clarification. I think I need to put this into the assignment description as well. This is a one and done submission. So the sooner you submit it, the sooner I'll try and grade it, so that the sooner you know whether you've mastered it or not. But you will not get more opportunities to submit it. So don't submit it until you feel quite confident. Review with other people. Bring it to the tutoring center. Really try to master this stuff. Okay. By the way, this is quite rare, so I just want to share it. My OChem 2 final had a perfect score. There was one student that lost 0 points.
I thought that someone did that on this test.
Do you see a 70 on the left-hand column? I don't.
Oh, no.
No. Somebody missed maybe 2 of the multiple choice to get a 66 out of 70, but not a perfect score. No, it doesn't happen very often. You know how hard it is to get a perfect score on a test like this? You miss one problem and you're done, right? There's no room for error. Hell, how many mistakes did I make? My exam wasn't even a perfect score, and I've been doing this for years. All right. I want to come back to the nomenclature that we have on there and start us off by looking at these problems on active, the ball and stick. So this is section 7 homework, problem number 2. It says this carbocation is an intermediate in a reaction with 2 different alkenes. Identify the 2 alkenes that would selectively generate this cation. So you know what? We're gonna touch on this a lot more today. Maybe it would make sense that I bring it up later. Essentially, what we are looking at here is an alkene in a reaction with an alkyl halide. At the end of last class, we took a look at how alkyl halides, and Patrick actually pointed this out appropriately, alkyl halides can react with bases to form alkenes. And we know that the alkyl halide has to react with a base because, as Patrick pointed out, we are always losing a beta hydrogen in order to form an alkene. And if the carbon is losing a hydrogen, that makes the carbon the acid. Something else must be the base. But this is a reversible reaction where alkenes can also be used to form alkyl halides. And oftentimes, what's in the middle is a carbon cation or a carbocation. We're going to talk about that a lot more today. So the same principle about alpha beta carbons applies. We were talking last week about how the alpha carbon has a leaving group, and the beta hydrogen is also removed. Those are the 2 groups lost in order to form the pi bond by elimination. And in the same way that we said, wherever the alpha carbon is, we can look around it, beta carbons, and those are possible placements for an alkene. This is the same thing, where the alkene is some sort of alpha-beta double bond that goes into a reactive intermediate that has a positive charge on one of those 2 carbons. And it doesn't matter. The alpha carbon is the carbocation or the beta carbon, doesn't matter. But what we're learning is that one of those carbons becomes this carbocation intermediate. So when we look at this, we have to really try and analyze it because they don't show us the charge. When we look at this, we got to try and figure out where that positive charge is. Well, it can't be on a CH3 that's bonded to the group. That's saturated, that's full. Can't be on this CH2 or any of these CH2s. And luckily, we can actually see the hydrogens. But here, I don't see a hydrogen attached. And I might assume that the hydrogen is behind it, blocked from view, eclipsed. But knowing that I'm looking for a positively charged carbon, this is probably the only 3 bonds going to that carbon. So that is either the alpha carbon or the beta carbon, doesn't matter. But the question then is, what alkene could have made this carbocation? First, it does help to take it out of ball and stick model and draw it as a bond line structure, the way that we've familiarized ourselves, because now we see there's symmetry. There are 3 total beta carbons, beta, 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 but 2 of those beta carbons are exactly the same. So forming an alkene to either of those beta carbons is the same alkene, 1-methylcyclopentene, actually. But the other beta carbon is unique, and forming a double bond there would be distinct. So this is the same thought process. I have a positive charge here. What other carbon could that positive charge could have been in an alkene with? Is this clarifying how to solve the problem?
Well, kind of, because I got one of them right, but the other one wrong.
So what were your options? What did you decide on?
I drew the carbon bond next to the methyl as a double bond.
Here.
Yeah. And that was correct.
And then you did?
And then I did just the other one.
The other side.
That was wrong. Yeah.
Do you see?
No, those are the same.
The same.
That's the same molecule.
So do you have to draw the double bond on the methyl?
Right. Which means make it no longer a methyl.
Right. Then it's
Now it's actually a methylene. This structure is called methylene cyclopentane. So we talked about nomenclature and how we want to put the longest carbon chain through the alkene. But in this case, I have a carbon of the alkene outside of the ring and a carbon of the alkene inside of the ring. And we also learned that we can't make a parent chain go both within and without of a inside and out of a ring. So my parent chain can't include the alkene. So we call the alkene a substituent, methylene cyclopentane. All right, the other problem, question 4, is a very similar approach, but this time it's the arrow is confusing. This time it's saying that this is the product from 3 different alkenes. And it's actually giving us where the halogen is. So the halogen has added to the alkene, which makes, we should assume then that the carbon the halogen is bonded to was one of the alkene carbons. That's alpha. We just need to look for the possible betas. Again, this is very similar to what we did last week, just in reverse. Instead of what alkenes could this make, it's what alkenes could have made this.
So we know that
You're still identifying 2 carbons next to each other. Once again, I think it's useful to take this and convert it into bond line form. So I've got a methyl group at this position 3, and then I have a bromine and an ethyl group at this position 1. If I say my bromine is alpha, alpha must have been one of the alkene carbons. So now I'll identify the beta carbons. Here's a secondary beta to the left, a secondary beta to the right, a secondary beta off of the ring. And unlike last time, going to the left on my ring is a different alkene than going to the right off of my ring. Last time when I went left or right, the symmetry meant that I had the exact same alkene predicted. The lack of symmetry here is what allows us to have 3 different alkene starting materials.
So if you took that methyl off the 3rd position,
Yes.
there'd only be 2.
Correct. This is essentially this problem again because of the symmetry. But now that I've made this carbon asymmetric to the ring, now there's different possibilities.
So do you remove the bromine from the question?
Yes, the question is asking, how did the bromine get there from an alkene? Well, this must have been one of my carbons of the alkene. So here are 3 positions next to alpha. Draw what the alkene would look like. Okay. Now let's jump back into our nomenclature. Cyclopentene. Why do I need no locant in this name? Absolutely. Where else would the alkene go? It's a ring. It's just going to go into the ring. What about 1-methyl-cyclopentene, which Elvira actually came back to add the 1 to it? Why does this need a 1? Because the substituent can't be assumed to be anywhere if I have to already assume the position of the alkene. The alkene gets to be assumed as position 1 because it's highest priority. And the alkyl substituent, I have to designate where it goes. It's either on position 1, or it's on position 3, or position 4. And those are all different, so I have to clarify with a locant for the methyl. Okay, 3-ethyl cyclohexene. We understand now why I don't have to say 1-hexene, but why can't I make that position 2, 1, 2? Have to count through the alkene. Good. 5-bromo cyclohexa 1,3-diene, which was a great fix. Earlier what you had, Delaney, was cyclo 1,3-hexadiene. But cyclohex is the root.
Right.
So the 1,3 comes after the root before the suffix. Hexadiene isn't the suffix. Diene is the suffix. Great fix. And why 5-bromo? Because I'm pretty sure that I could get bromo to be at position 1 if I started numbering there and then into the alkenes. Okay, the alkenes are the higher priority, so I need to start numbering at the alkenes. But I still could have gotten my bromine on position 3 if I started at this alkene.
But then that puts the other alkene at a lower priority.
I have to prioritize both alkenes before I pay any attention to the alkyl halide. But there are 2 ways that I could get the same priority for the 2 alkenes, correct? I could start where we did for this one. I forgot who named this. Oh, Delaney. I could start where Delaney did, and I could get the alkene at 1, 3, and the bromine at 5. Or I could start the other way and get the alkenes at 1, 3, but the bromine at 6. So this name is actually prioritizing the 2 alkenes, and then from the 2 options that give a tie, prioritizing the alkyl halide. There's 2 ways that I could get cyclohexa 1,3-diene, and I'm choosing the one that gives the lower locant for the bromine. So I'm prioritizing both. I just have to prioritize in order.
Can I fix one of mine real quick?
No, but I'll fix it for you when we get to it. All right, so this one, we've got 6-isopropyl, 3,3-dimethyl, cyclohex 1,4-ene, diene. So the only change there would be cyclohexa 1,4-diene. Now this one, doesn't matter where you start or how you go, you're going to get 1,4-diene. So then it comes down to the locant set for the alkyl substituents. If I start on the bottom right and number clockwise, it's the same locant set I get as if I start at the bottom right and number counterclockwise. And then if I start at the top right and go clockwise, or the top left and go counterclockwise. So I really have two sets here. I could either get the methyls at 3, or I could get the isopropyl at 3. So my locant set is 3, 3, 6 for the 2 methyls and the isopropyl, or 3 for the isopropyl, 6, 6 for the dimethyl, and I go for the lowest locant set. Once again, even though I've already prioritized the diene, I'm now choosing the lowest locant set for my other groups.
I was literally just about to ask that. It doesn't matter which one we prioritize or.
First, prioritize the alkenes. And if there's more than one route that gives the same lowest locant set, then go down to the next priority. So we look for the lowest locant set at the first point of difference for the highest priority in order as many times as we have to. All right. For the top right, 3-methyl tetrabutene. What's the tetra mean? Quinn, what's that one, yours? Top right, Liana. Tetra, 4. Well, you already have bute. So the tetra would be like tetraene or tetramethyl, so we don't need the tetra. But we do need a locant for the alkene. Since I'm not in a ring, my alkene could be at position 1 or at position 2 in this 4-carbon chain. So I could call this 3-methyl 1-butene. The tetra isn't necessary there, though. Or actually, the tetra is wrong.
It have to be 1-butene though, right? Because
Well, it could be 3-methyl but 1-ene. But yeah, it has to be position 1 because that's prioritizing the lowest locant set for the alkene. 2-methyl prop 2-ene.
I want to change that to 1.
Good, good. Because the way that you numbered it was starting this way, putting the alkene at position 2, instead of numbering it this way, putting the alkene at position 1. It kept the methyl at position 2. It just didn't minimize the locant set for the alkene. 2-methyl prop 1-ene. Great. 4-bromo 2-pentane. 2-pentene. Good. And there's actually a little bit more than we can add here. This pentene can either be a cis-pentene or a trans-pentene, an E or a Z. Which label should we add to it? Z for Zame side. Yeah, it's trans, opposite. The high priority groups are on opposite sides. High priority here is carbon, high priority here is carbon, going opposite ways. E, 4-bromo, 2-pentene. And great job prioritizing the lowest locant set for the alkene. All right, for this one, 3-chloro hex 3-ene. Once again, we need to add E or Z, cis or trans. But this time, chlorine is the high priority group, and carbon is the high priority group. So this is a cis alkene or a Z alkene. So a better name here is Z 3-chloro hex 3-ene. Now in this one that Andrew named, he had to start from the right to prioritize the alkene at position 2 instead of 3. But for this next one, whether you start from the right or start from the left, the alkene is at position 3, so that's a tie. And then we prioritize the next locant, the next lowest group, the chlorine. All right, this one nobody named. The longest parent chain, though, is actually the alkene, which makes the ring a substituent off of it. So this compound is Z. I've got a methyl and a cyclopentyl. So 3-cyclopentyl, 4-methyl. I ran out of space already. pent 2-ene. Sorry about how that looks. Okay, with drawing a compound, Delaney, are you all right with?
Sorry.
Do you know? No, it's good. Do you know what? It's not Z. Sorry, this is actually a trans alkene. High priority here is carbon over hydrogen. But the high priority between what looks like an isopropyl and the cyclopentyl, they're both connected by a tertiary carbon. That's not a point of difference. But then cyclopentyl has secondary carbons, and isopropyl only has primary carbons. So the high priority group is cyclopentyl. So the priorities are trans. When you're drawing a compound, no, it's okay.
I was just, okay, what's happening with the Z3-chlorohex-3-ene with your arrows?
I'm just saying, here's the high priority group, here's the high priority group. They're pointing in the same direction off the alkene. Same thing I'm doing here, different directions, different directions. When drawing an alkene, or when drawing a structure, I like to start with the root, the parent chain, and then go in and add everything else in off of that. So bromoethylene, well, eth is a 2-carbon, ethylene, a 2-carbon alkene. There's a reason that this doesn't have a locant. There's only one type of position it could be on, one bromoethylene. This is also referred to as vinyl bromide. If that were a chlorine instead, we'd have vinyl chloride. And if you polymerize vinyl chloride, you get PVC, polyvinyl chloride. All right, this one, I'll start with the root, bute. I've got an alkene at 1. There's my bute-1-ene. I've got a chlorine at position 3, but specifically, I want an R configuration. My highest priority group is the chlorine, then the carbon of the alkene over the primary carbon, 1, 2, 3, looks clockwise. If it were a clockwise rotation, that would already be R if the lowest priority were backwards, the hydrogen. So by making the chlorine wedged and putting the 4th priority back, I've created an R chiral carbon. You guys remember doing this on the Unit 2 test. Okay. E2-butene, this one is pretty simple. We've already looked at it. I actually do want to point out, if you take my advice here and you say 4-carbon chain, that's the root, the parent chain. At position 2 is an alkene. What would you do if you had drawn this, but you were asked for cis-2-butene? That's not cis. Yeah, so then you just take one of the 2 groups, or sorry, you take 2 of the 4 groups, and you just flip them. Okay, here's how that actually applies back to the R. What if I was doing this, and I just said, I don't know whether the chlorine should be wedged or dashed. I'll just make it wedged. And then I go in and I look, and I see 1st priority, 2nd, 3rd, clockwise, R. Oh, it's already good. It's already what I want it to be. If it was wrong, I would just take 2 of the groups and flip them. Same thing happens with the alkene. If the stereochemistry is wrong, just take 2 of the groups and flip them, and you've changed the stereochemistry. When we say that the number of stereoisomers, I think you guys remember this little equation, is equal to 2 to the n, and n is the stereocenters. Alkenes can count as stereocenters. An EZ alkene now becomes a stereocenter. So there are 2 stereoisomers, 2 to the 1 stereocenter. Here we've got an S chiral carbon and a Z alkene for 4-methyl hex 2,5-diene. All right, well, here's hex. I'll start with the 2,5-diene. So carbons 1, 2, 2 to 3, 3, 4, 5, 5 to 6. All right, well, I can see that one of my alkenes is not a stereocenter. One of my alkenes is neither E nor Z. It's not cis or trans. Why? One of the groups, one of the carbons, has two identical groups. And we said that in order for an alkene to have E or Z stereochemistry, one of those two groups has to be, both carbons have to have two distinct groups. So this carbon, this alkene is definitely EZ alkene because both carbons have two distinct groups. Is it already shown as Z? It's not. Like up above, it is shown as E because that is just how I drew my 6-carbon chain and then put the alkene in. So I need to take one of the carbons of the alkene and swap its two groups. I could take the hydrogen and the rest of the carbon chain and swap them. That just seems like a lot of work. So I'm going to take the methyl and the hydrogen and I'm going to swap them. It wouldn't matter how I do that because either way I'll end up changing the configuration. Okay, so I've made my Z hexa, that's a problem, hexa, 2,5-diene. But what about my 4-methyl? 1, 2, 3, 4. Here's my 4-methyl. And I need my 4-methyl to be S. Oof, so let's just do what I did before. I'll make it wedged, and then I'll check. Lowest priority is the methyl group going backwards. No, sorry. Lowest priority is the hydrogen going backwards. And then I've got carbons all the way around. So at some point, a carbon is going to end at a hydrogen, and that's going to give it a lower priority. Carbon, 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 no point of difference. Hydrogen, carbon, carbon, that's a point of difference. So this actually becomes the lowest priority group 3. And then again, carbon becomes hydrogen, carbon turns into another carbon. So here's the highest priority and the second highest priority. Remember, it's highest priority, highest atomic mass at the first point of difference, no matter how far down the chain you have to go. And in this case, we just go down the chain until we run out of carbons. Whichever group has the last carbon standing, that's the highest priority group. All right, 1, 2, 3, counterclockwise. That's S. I nailed it, and I completely guessed. And if I had not nailed it, I would have just erased the wedged methyl and drawn in a dashed methyl instead. And that would have flipped the configuration to be what I needed it to be. Okay, last one, 3-bromo, methyl cyclopentadiene. No numbers given on cyclopentadiene. So there's only one configuration of cyclopentadiene. There's not two ways that you can configure it. Here we've got cyclopentadiene. If this is position 1, because that's where methyl is, which way do I need to move? I have to move through the alkene. So I have to move this way. Position 1, 2, 3. What you've drawn is 4-bromo, 1-methyl cyclopentene, which would have actually been better named 1-bromo 4-methyl. Since I could have started at either of these and gotten the same locant set. A tie locant set goes to the first alphabetically. So this just has the bromine in the wrong spot because it assumed starting at a carbon but not going through it. The right answer here has bromine down there. Okay. Feel good on nomenclature? Love it or hate it? Feel somewhere in between? Yes?
Sorry, this is kind of backtracking a little bit, but what are the rules for
highest priority, highest atomic mass at the first point of difference. So like here, highest atomic mass was either carbon, carbon, or carbon. The lowest atomic mass was hydrogen. But that's not different, so I find the next highest mass in the chain. After carbon, the next highest mass is hydrogen off of the methyl, because there's no other carbons.
Right.
But here, the next highest atomic mass is carbon. Same thing here, the next highest atomic mass is carbon. So that's not a difference. Here, the next highest mass is hydrogen. Here, the next highest mass is carbon.
So you can always just do it off of mass.
It's only off of atomic mass,
Okay.
not a group's mass, but an atomic mass.
Okay.
And then the Z and E, that's only off of alkenes and the groups coming off the alkenes?
Yeah. E and Z describe how the groups are arranged around an alkene.
Okay. And then is it like groups of the highest atomic mass as well, or other?
Yeah, when we had this structure, I'll redraw this so we can visualize it a little bit more clearly. We had an alkene, and one direction had this isopropyl, and the other direction had this cyclopentyl. So how do you decide which group is high priority and which group is low priority? We decide priority by highest atomic mass at the first point of difference. So off of this alkene, carbon, we've got carbon or carbon, not a point of difference. Or we've got a secondary carbon and a secondary carbon. Now that's technically not a point of difference because carbon has the same mass as carbon. But after a secondary carbon, I have another carbon. After a primary carbon, I have just a hydrogen. So I could actually lean into saying a secondary carbon is higher priority because it is going to have more carbon than a primary carbon. It's going to have less carbon. It's going to run out of a higher atomic mass sooner. But it's always highest atomic mass. Okay, let's go back to talking about what alkenes can do. By the way, does anybody need the worksheet that we were working on from last week? Has this energy diagram on it. Okay, what can we do with alkenes? Well, first of all, I want us to recognize that we can do resonance. I know it seems odd, but we can take an alkene and we can say, what if the electrons localize themselves on specific carbons? By the way, I don't ever recommend taking one resonance form in the middle and showing arrows to more than one resonance forms on the sides. So we could add an electron arrow here that shows the electrons moving one direction or the other. But that would only help us show how one of them is formed. So I'm just going to show the arrow that helps us generate the form on the right. If the electrons were to be taken by that carbon on the top, it would leave a positive charge in the middle. We call a positively charged carbon a carbocation, and we call a negatively charged carbon a carbanion. And what you should see in those words, cation, anion. What did you first read it as, Elvira? Carbocation. I'm excited. 2 weeks from now, I'm leaving on a nice carbocation. Very common mistake. Carbocation. Okay, we know that this resonance form in the middle is the major resonance contributor. We know that the molecule looks mostly like this. But which of these resonance forms would the partial charge best represent? Partial charge? Do you know what causes partial charge? Dipoles, polarity. Yeah, an unequal sharing of electrons, which is usually caused by a difference in electronegativity. What's the difference in electronegativity between carbon and carbon? So why would there be any partial charges? There's some partial charge because of electron repulsion, essentially electron repulsion and induction. So we're going to look at this and we're going to analyze for electron repulsion and we're going to look for induction. Do you remember what induction is? Not necessarily. One of the ways that we look at induction is how close is it to an electronegative atom. You saw that on your midterm. There were two carboxylic acids, which meant they had the same atom that was acidic, they had the same charge, they had the same amount of resonance. They were donating from the same orbital, but one of them had better induction because of its proximity to an electronegative atom. Induction is a pull of electrons if there's an electronegative atom nearby. Induction is a push of electrons if there are not very electronegative atoms nearby. Induction is a push or a pull of electron density. You guys have used an induction oven? No, an induction stovetop before? Or what do they say when people go into labor? They induce labor, they had an induction done. So induction is this making something happen. What are we making happen? We're making movement of electron density happen. We're pushing electron density this way. We're pulling electron density this way. Either way, it's a push or a pull. So I want us to look at electron repulsion and electron induction. Okay. On the left, is this how I gave it to you? Negative on the left? That's great. On the left, I want you to look at that lone pair on that carbon. And I want you to think about how much electron density is around it. It's a lot. There's a lot of electron density around that lone pair. You see how that lone pair on the tertiary carbon is surrounded by all of these groups? And all of those groups have electrons already. So we're putting all these magnets next to each other and we're getting all this repulsion. The lone pair, if it gets pulled into that center carbon, it gets pushed away. This has high electron repulsion. Meanwhile, if I put the positive charge there, well, that positive charge does not experience repulsion, does it? Instead, the positive charge is looking for electrons to come and satisfy it. The positive charge is actually pulling electron density towards itself. So the more electron density surrounding it, the more that positive charge can get stabilized. I like to think of this as moral support. You're broke, so all of your friends pitch in $5. The more friends you have, the less broke you are. How many friends does this broke guy have? Not a lot of friends. It's got hydrogens bonded to it, but those hydrogens don't have a lot of electron density to donate. How many friends does this broke guy have? A lot of friends. Yeah, it's got these two big carbon groups and all of the other electron density from these things. This is what I would say is that this has, we're going to give it a new name. This is not a name that I'm inventing. We call it hyperconjugation. But you can think of this as induction, a stabilizing induction. You guys remember conjugation? Conjugate your verbs. Ran, run, runs. You conjugate your acids and bases. An acid becomes a conjugate base. A base becomes a conjugate acid. You conjugate atoms through resonance. There's a relationship between atoms. Conjugation is a relationship. The hyperconjugation here is just the fact that nearby surrounding electron density can be used as this sort of shield on that positive charge. Okay? Oh, also, what about the negative charge? Does it have as much electron repulsion as before? No, it has far fewer groups surrounding that lone pair. That negative charge has just these hydrogens, which remember has very little electron repulsion. So this has high hyperconjugation and low electron repulsion. This one gave our lone pair high electron repulsion. What about hyperconjugation? It gave very low hyperconjugation. Can you see how this is a win-win or a lose-lose situation? Either the negative charge is highly repelled by neighboring groups and the positive charge is not well stabilized, or the positive charge is well stabilized and the negative charge is not highly repelled.
I thought dipole moments pointed towards the negative charge.
Dipole moments point toward where electrons are moving.
So why wouldn't they point towards where they were lower?
These electrons, bonding carbon and hydrogen,
Where they want to move?
those electrons are being pulled in toward this vacancy.
Oh, okay, that makes sense.
Good, great question. You see how it's a win-win or a lose-lose? So, which of these resonance forms would best predict partial charges on this alkene? The one on the right. The one with the less substituted negative charge and the more substituted positive charge. So this is what I want you to take away from this. This alkene has partial charges. And you would have never predicted that because there's no difference in dipole, but there is partial charge. Is it surprising to you that the positive charge and the negative charge have different places where they are more stable? Positive charges are more stable on more substituted carbons. And we're going to do a lot with positive charges. We're not really going to do that much with negative carbon ions. Not this semester anyways. But is that any surprise to you that a positive charge is more stable on a more substituted carbon and a negative charge is more stable on a less substituted carbon? Yes? No? Surprising? Not surprising that the two different charges have two different regio-selectivities? They're opposites, right? Opposite charges should have opposite stabilizing factors. What stabilizes a lack of electrons is not what should stabilize an excess of electrons. How do you stabilize a lack of electrons? Swarm it with electrons. Make it not even know that it lacks electrons. How do you stabilize an excess of electrons? Get it as far away from other electrons as possible. What's good for a positive charge is not what's good for a negative charge. Of course, they're different charges. All right. Now, with what we've just learned here, I'd like you guys to think about partial charges on trans 2-butene. Can you predict anything?
It's gonna be the same either way it breaks.
Yeah. If I put the lone pair on one carbon and the positive on the other, that's a secondary carbocation and a secondary carbanion. And if I flip it, it's exactly the same. So partial charge, not easy to predict. It's like they're both partial negative and both partial positive. What about on that 2-methyl-1-butene?
Positive charge would be on the second carbon.
More substituted, less substituted. We can predict charge placement, partial charge placement, by the substitution of the carbons. No partial charge preference on the left, and a partial charge preference on the right. We have a term for this. Yeah?
So basically, the carbon that has like the more friends, you give like one you rather than the one that has less friends, you give.
Yes. Carbon with more friends, more positive. More money, more problems. Okay, we have a term for this. We call them unsymmetrical alkenes. Unsymmetrical alkenes have a more substituted carbon and a less substituted carbon. And that's what makes them unsymmetrical. So that the two carbons of the alkene have different number of carbon groups coming off of them. Which would imply that a symmetrical alkene even if the two groups are of different size, even if the two groups are different from each other, meaning even if there's not actually symmetry in the molecule, we still call it a symmetric carbon or a symmetrical carbon because they have the same substitution. An unsymmetrical alkene, we can make predictions about partial charge. A symmetrical alkene, there is no prediction, so there's no regiochemistry we can predict.
So despite that one having an extra carbon on the left side,
Mm-hmm.
because it's still a secondary carbon, it's gonna be equal. They're both secondary carbons.
Yes. Even though this is essentially an ethyl versus a methyl, the two carbons have the same number of carbons coming off of them. So we can't make any predictions about regiochemistry. What I mean there is, when an unsymmetrical alkene reacts, we can say things like Markovnikov addition. The H adds to the carbon with more H. And we know that we'll have regioselective products. When I have a symmetrical alkene, I can't say Markovnikov or anti-Markovnikov because both carbons have the same number of hydrogens. So it's not adding the hydrogen to the carbon with more hydrogen. It also means I might get regio products that both form, but give different molecules, give different answers. I don't know if you guys are picking up on this, but we're calling it unsymmetrical as opposed to chiral or asymmetrical, because we already said chirality is asymmetry, but alkenes are planar, which means they have symmetry. Their top is identical to their bottom. They exist in a plane. So we can't call them asymmetric alkenes because they are achiral. They are technically symmetric, so they call it unsymmetrical. Love it. All right. The idea that an alkene can form a carbocation is well studied, well understood. We will form a lot of carbocations from our alkenes. And so I want to take you to what we have on the bottom here. On the left, I want us to propose that we are working with 2-methyl, 2-propene. No, sorry. 2-methyl, 1-propene, 2-methylpropene, and hydrobromic acid. What type of reagent is hydrobromic acid? It's in the name. It's an acid. It's an acidic reagent. If HBr is an acid, the question we should be asking is, what's the base? If HBr is an acid, what's the base? There's not a lot of options. If HBr is an acid, what's the base? The alkene. If HBr is the acid, then HBr can't be the base. By definition, it has to be the acid. So we only have two things here, the alkene and the acid, so the alkene must be the base, right? How will that base react? We've already discussed this. We said there's two ways that the alkene can act as a base. The first way is if the primary carbon or the more substituted carbon, oh, you know what? I got ahead of myself. I want it, we'll come back to it. We could say the less substituted carbon acts as the base and takes the hydrogen, leaving behind a positive charge on the more substituted carbon. Or we said the more substituted carbon could take the base, could be the base and take the hydrogen, which would leave behind a less substituted carbocation and bromide. You remember we talked about this when we did mechanisms last week. We were looking at how one arrow pushing doesn't really make a prediction about which carbon uses the electrons. There's two possibilities. Both carbons could use the electrons. Knowing what we know now, we learned that this carbon is partial negative and this carbon is partial positive. Who gets to use the electrons? Why? It needs them, but does it really want them? It's already giving them up. That's why it's partial positive. It doesn't have control over the electrons. Who has control over the electrons? The partial negative. So who gets to use the electrons? The partial negative. No. It's really not. Every time you've seen a partial positive and a partial negative, the atom that keeps the electrons is the partial negative atom. A carbon-bromine bond breaks. Which way does it break? Toward the partial negative. A CO double bond breaks. Which way does it break? Toward the partial negative, towards the oxygen. So a partial charge on an alkene tells us the same thing. The partial negative, and this is not the first time I've heard that it feels unintuitive. This idea that, oh, the positive carbon must want them back, that's a common idea. It's partial positive because it's already willing to get rid of them. Partial negative uses the electrons, and what do we end up with? A more substituted carbocation. Why is that at a lower energy? Because a more substituted carbocation has more hyperconjugation, which stabilizes it. A less substituted carbocation has less hyperconjugation, less stabilization. So two things can happen. Which one will happen? The one that takes the least energy. The one that forms the lowest energy intermediate. Because if I have enough energy to do this dotted pathway, I already had enough energy to go over the full pathway. So if I have enough energy to do this, I already did something else. More substituted carbocation always forms, which means the product that we get here shows the bromide bonding with the more substituted carbocation. The product that we do not form is where bromide bonds to the less substituted carbocation, because the less substituted carbocation doesn't form, because it takes more energy, it goes against stability, it goes against partial charge, and for another reason. Carbocation rearrangements. I'm going to leave this because I'll come back to it at the start of class tomorrow when we wrap up this worksheet, and it should feed well into the activity that, the worksheet that we do tomorrow. But carbocations, remember that carbocations are what we call reactive intermediates. They are formed, but they don't last long before they react with each other or react with something else. Carbocations can rearrange, meaning if there is a less stable carbocation that forms and it's close enough to a carbon that would be a more stable carbocation, we see electrons shift to put a vacancy carbocation in a more stable position. We see the structures rearrange. We'll talk about that rearrangement. I actually want to come back to talking about alkenes, because this will be a good way to wrap up today's lecture. Stability of alkenes. Hey, you know, we have a regio term called Zaitsev elimination, and Zaitsev demonstrated that the most stable alkene is the alkene that preferentially forms. So how do we know the stability? The least stable or the most reactive is actually directly in line with the least substituted. Most stable, man, I'm sorry about these markers. Most substituted. Well, when we talk about substitution in terms of alkenes, alkene describes two carbons, so I'll have to follow the substitution of two carbons. A non-substituted alkene, that's an alkene that has no carbon groups coming off of it. That's ethylene, which is so funny. Yes, we could have called it ethene, two-carbon alkene, ethene, but its common name is ethyl, as in a substituent. Ethylene, a two-carbon alkene.
So like for what we do with naming, so instead of propene, would it be propylene instead of, or no?
You can call it propylene. That's also common. But they don't commonly call it butylene or pentylene or hexylene. Just ethylene and propylene, they do that. But it's also just as good to call it ethene and propene. Non-substituted. But also, if I put on halogens there, like vinyl chloride, that's non-substituted because there are no carbons coming off of the alkenes. Monosubstituted means that one of the carbons has one carbon group. Propene is a good example here. Or as you said, Patrick, propylene. When we get to di-substituted, okay, you guys are catching on that we're using different terms, right? It's not primary, secondary, tertiary, quaternary. It's mono, di, tri, tetra. When I get to di-substituted, there are 3 ways that I can arrange 2 groups. First, I can have one group coming off of each carbon, and I can either have that cis or trans. Which one am I saying is more stable? Trans. Why is cis less stable? Why is cis higher energy? Because if it's cis, I get more steric strain. Torsional, remember, is the eclipsed electron pairs, and the alkene doesn't really have any way around that. But if it's cis, I get more steric strain, and if it's trans, I get less steric strain. First time I ever cried in class was when I was asking a class this, why is cis less stable? And in unison, they all said steric strain. And I was like, oh, did I teach something? And then I was like, oh, you guys all read the book, didn't you? And they said, no, you just talk a lot about steric strain. There's that steric strain. You see it?
Well, they're eclipsed, so it would be torsional strain.
But that's true of both of them. So,
Doesn't 2R groups have more torsional strain than an R and an H group?
good question. No. Because the torsional strain is actually these electrons and these electrons. So these hydrogens have the same amount of torsional strain as these, because it's not about what group is connected. It's just about the fact that the electrons are stuck eclipsed with each other. And the alkenes have no way around it. So torsional is the electron repulsion you get from rotating. Steric has to do with the size of the group. Okay, there's another way that I can arrange 2 groups. I could have both of the R groups coming off of the same carbon. And that is a more stable configuration of di-substituted than these other 2 possible ways. And it has to do with the charge separation. Here you don't really get a stable partial positive or a stable partial negative, but with this you do get the most stable partial positive and the most stable partial negative. So this is the most stable because of how it separates charge. A way that you could differentiate these, I like to say that these are internal di-substituted, and this is terminal di-substituted. Is it clear why I call them that? The terminal di-substituted ends at a CH3. The carbon chain ends at the alkene. An internal di-substituted group, the alkene is just part of the carbon chain. It's not at the chain, it's not at the end of the chain, it's somewhere in the middle. I ran out of space down there, but what comes after di-substituted? Tri-substituted, and then what comes after tri? Tetra. On the front side of your worksheet where we have all those alkenes, how many tetra-substituted alkenes? On the front side, where we named them. Just from the drawings, you don't have to look at the ones that we actually had to draw. From the ones that were already drawn out, how many tetra substituted alkenes? 0. How about this cis 3-chloro-3-hexene in the middle row, second from the bottom? Primary, mono, di, tri, or tetra substituted? 3-chloro-3-hexene. Tri substituted. How many carbon groups coming off of the alkene?
3 is done.
Chlorine is a carbon group?
Oh, no.
Right. Chlorine doesn't count. Just like how vinyl chloride is a non-substituted alkene.
So the R groups have to be a carbon group,
Correct.
not just any R group.
Correct. In these cases, R has to be a carbon group. Good. Okay, and then cyclopentene. Mono, di, tri, or tetra. Cyclopentene. Cyclopentene is a di substituted. Good. Okay, so when we come back tomorrow, we're going to talk about stability of carbocations. And spoiler alert, the most stable carbocation is the most substituted carbocation. So we're just seeing a repeat of that trend. Then we're going to talk about how carbocations can rearrange to become more stable. And with that, we will start going into our alkene addition reactions. In fact, if you guys would like, I've got the packets already. And this might be useful for you as you start doing the active homework and preparing for the unit test this weekend, because I've listed out an example for each of the 12 reactions that we're learning this week. We're learning 12 reactions. You need to be familiar with the reagents of all 12 and the products that they form, the functional groups they form. But you only need to be familiar with 4 of the mechanisms. And really, it's 2 sets of 2. Like 2 of the mechanisms are so similar. 2 of the mechanisms are so similar. So we're learning a few mechanisms this week. We're learning these reactions. Would anybody like one of these ahead of time? Okay. Okay, thank you guys for your time. I'll see you tomorrow when we start going through our addition reactions. Welcome. Andrew, do you want one of these? Or do you want it tomorrow?
I'll take one.
Sure. You're welcome. Would you guys like these ahead of tomorrow? Yeah.
Can that be rice, or why not?
No, because we give the locant of the alkene to the first carbon.
Oh, could that be right?
Yes. 3-ethyl hexa-1-ene.
But we don't have to, because we know that it's always going to be that, so it could just be 3-ethyl.
Hexene. Yep. The one is implied.
Yeah.
Oh, actually, that's yeah. The A wouldn't be there.
So it'd be cyclohexene.
Cyclohexene. 3-ethyl cyclohex-1-ene.
So, but
3-ethyl 1-hexene, 1-cyclohexene, or
could
but
say
the
3-ethyl
cyclohexene.
1-ene.
Cyclohex-1-ene. That's the other thing that's missing. Cyclo's missing. Yeah.
How long are we at today? Is it pretty long from last time?
It actually, it goes faster than you'd think, despite all the things you're going to do.
Okay.
So,
Quicker than last time?
sorry.
I was just confused about what's happening with these X's and checks.
So your arrows are starting at the right place, but they're ending at the wrong place.
This one goes to there.
And the OH bond does break. We see that it
Yeah.
breaks. But who owns those electrons? Oxygen. So the electrons,
Oh, they gotta go from oxygen to the hydrogen.
the electrons are shared between O and H, and then they are taken back by oxygen.
So it goes like here.
So the line
Sure.
to the O.
Or, yeah, just starts there and points at O.
starts here.
The bond does.
Starts at the bond.
And then the
Goes like that.
alkene goes to.
Yeah. I feel like you're going like
H.
towards the alkene, but there is no interaction between these electrons and the alkene. These
No, because
electrons,
that's this.
yeah, these electrons are owned by oxygen.
Yeah.
Oxygen is not going to just lob them over
Right.
to a carbon. But how does this carbon get the hydrogen?
From,
What carbon got the hydrogen?
The carbon on the bottom goes from CH to
Oh,
CH2.
right. So the alkene points to the hydrogen.
Good.
so that's like that.
Yes.
And then I did this one wrong.
It starts from the pi bond, but where does the pi bond attack? It wouldn't matter which hydrogen you choose, but whichever hydrogen you choose, break that bond. Do you see?
So it should go to that one.
Yeah, yeah.
If I'm gonna break that bond.
I have a question. So we get half points back on the ones we missed.
Mm-hmm. You can
So-
earn up to half the points back.
So it's out of this number, not with the bonus.
Yeah, yeah.
Okay,
Mhm.
great. Great.
I basically had the same question, so this pi bond should be going to a hydrogen.
Yes.
Then I needed a line showing this electron going to the oxygen.
Do you see how this arrow starts at the hydrogen atom,
Yeah,
which is not a source of electrons?
no, it's always a proton.
Yep. No nucleus, no chemical symbol is a source of electrons. Lines or lone pairs
Yeah.
are sources of electrons.
I understood that a lot better after the midterm when we were talking about electron arrows. Thank you, Professor.
You're welcome. And I am glad that it's starting to click more since we've gone over it more. But I worry that if I didn't take the time to put it on the midterm, it would have made less sense. Like, would you agree that seeing it on the midterm kind of pushed you to